Hei, og velkommen til denne aller første episoden av Delta P, spoken entirely in English. The Trondheim Science Week are upon us, and I've got two very special guests here today. First, we got a scientist working at the Andøya Spacecenter, where he's teaching students stuff he wished he'd learned himself a long time ago. At the Trondheim Science Week, he held a great lecture about maths and the human imagination. Give a warm welcome to Alexander the Great B. I'm sorry, how do you pronounce
Biebricher.
Biebricher.
Yes.
That's a German name.
That's a German name. I am a German.
You are a German.
Yes, but halfway Norwegian already. After 15 years here. So.
That makes kind of sense.
Yes.
Very good.
Yeah. Thank you
and on my left, oh, it's on the left. I've written left. That's perfect. We got from the exotic other side of the pond. She came all the way from the United States just to talk to me and my super podcast here at Delta P. Greetings to NASA's very own astrochemist, Stephanie Milan.
Hi.
Hi.
Thanks for having me.
Anyways, so Stephanie, is it okay I call you Stephanie?
Yes, please.
Yeah. In the movies, we see like when they launch a rocket, for instance, people throw papers and kind of everybody is excited. Is it like that?
Absolutely.
It is?
Yes. It's a culmination of years and years and years of work to get a rocket launched, a new observatory launched in space, a new mission launched. Sometimes these things start 20, 30, 40 years ahead of when that actually happens. So to see it get on a rocket and to be launched successfully into space is a huge ordeal.
So there is this real joy.
Yeah.
For you and Andøya, you do rockets too, right?
Yes, we do. We launch sounding rockets from there, as they're called. So they are suborbital. We do not launch things yet, I should rather say, actually, into orbit. For that, you would need, the big ESA or NASA rockets, because you launch the rocket up and then you play catch up with the Earth's rotation, which we don't yet do, but there are plans.
There are plans. You're actually planning to send big rockets from Andøya.
There are plans, yes. There are plans, but they're not very, they're not in such a way that I can say too much about them, but there are plans, yes.
Yeah.
But the two of you, we have you're an educator mostly, as far as I know.
Nowadays, yes, yeah.
Nowadays you are. Mm-hmm. You're an astrochemist. But have you guys actually been involved in getting rockets launched to some degree?
I'm working on a mission right now that will be launched in October of 2018. So that'll be my first full participation in a mission, and that's the James Webb Space Telescope. So it'll be actually launched from ESA on an Ariane 5 out of French Guiana. So I am very much looking forward to watching this mission get launched and successfully deployed and start its orbit at the second Lagrange point sometime in 2018.
Mm-hmm. Well, I have to ask, I'm so sorry, because I have to ask there, what do you do on the James Webb Telescope? Because I'm really excited about this thing being launched.
Me too.
And I'm so honored to actually be in the vicinity of someone who's working on this. What is it you do?
So I'm one of the project scientists. I was hired to be the planetary scientist for the James Webb Space Telescope. Now, this is an astrophysics mission that's been designed and optimized to detect the first stars of the universe. But being a planetary scientist or somebody that looks at things in the solar system, we want to be able to use this observatory just as we were able to use Hubble and Spitzer, for example, or even Herschel or other space observatories. So it was my job to make sure this extremely sensitive, floppy telescope that's pointing at the farthest reaches of the universe can actually look at the biggest, brightest, fastest moving objects in the sky. Things like Mars, Jupiter, Saturn, Pluto, comets, asteroids, basically everything beyond Earth, because we can't point towards the sun, so no Venus or Mercury or Sun. But so that was my job, to take an extremely sensitive instrument and make sure we can look at bright, extended objects.
Yeah, but just for those who didn't attend your lecture this day, What's the big difference between this telescope and the Hubble, which we used?
So James Webb is actually optimized in the near infrared. Hubble was more an optical and ultraviolet. It did go into the near infrared with 1 or 2 instruments. So James Webb is moving to longer wavelengths. So whenever you're looking for objects that are very, very far away in the universe, we look for things called redshifts. So this is where the actual atomic lines actually move in frequency or wavelength. So whenever we want to see something all the way at the other side of the universe, we're looking for extreme redshifts. And those shifts actually take optical lines and move them all the way into the near infrared and the mid infrared. So that's what we're aiming to do, is look for the very first stars, first galaxies of the universe, which have extreme redshifts that are actually closer to the near infrared.
Only?
No, not only. Just some of the easier ones to detect.
But so then when we see pictures of the objects furthest away, we're not going to see those nice optical images like we get from Hubble.
Well, so we will be doing imaging as well. It's just not going to be optical imaging. So if you've looked at images that have come from things like Spitzer or from the ALMA telescope or any radio telescope, we can actually image with those as well. It's just a different wavelength. It's the same thing as whenever they take a Hubble image and they combine multiple colors. They're just different wavelengths that they're actually making these images out of. So that's effectively what we're going to be doing, is taking an image just at a different wavelength. So it's not something you would see with your own eye, but then again, you wouldn't see it anyways because it's all the way across the universe.
But then here, a question I think both of you can answer. Is there a limit to how much we can see here from Earth? Because we keep developing better and better telescopes, but is that going to stop sometime? Is there a place, because of some physical limit, that we just can't look any further?
Well, I think the first thing you have to think about here is that when you talk about telescopes, you either put them on Earth and then you can build them rather big, but you'll have the atmosphere between you and what you observe, which makes some trouble. Or you put them into space, like Hubble or the James Webb telescope, but then you have to get them up there. And then you have the limitations of the actual technology that's behind that. So that's where the starting point, right? And I'm sure there are even more technical limits to the whole thing, I think, that you probably...
Yeah, absolutely.
Yeah.
So even though James Webb is the largest space telescope ever being built, it's a 6.5 meter diameter primary mirror. It has to fold up to fit on the largest rocket that we have on Earth. So it's actually a full origami telescope. It unfolds from a complete tight little package to a sun shield that's the size of a tennis court and a 6.5 meter primary telescope. So, I mean, it's extremely massive. It would not fit on any rocket as it stands in a fully deployed mode, so we have to fold it up. There's a lot of talk going on about the next telescope after James Webb, and some people are really interested in making the next Hubble telescope so that actually operates in optical and ultraviolet, and they need it to be even bigger. Yeah. So now we have to think about new ways to fold even a bigger mirror. And what kind of optics it's going to have,
so
etc.
that's just what you do. You just build one and then you want to build it bigger.
Well, we always want more.
Yeah.
But it's interesting, right? I mean, the limitations at this point in time is actually, the transportation and everything that's around it. So I think we could build, and we have built on Earth, bigger telescopes than James Webb, for example.
Yeah, absolutely. They're building a 30-meter class telescope, so... Yeah,
so if there was no limitations of bringing it up, what's the limit then?
I don't even know how to answer that properly.
We don't know.
We don't actually know. It's probably the best answer to give there, because you're not in that position to really have to judge that.
That's not a problem.
Right. Yeah, because it's like, I mean, when you work at NASA or you work with these kind of projects, you have very limited time, so you probably spend time thinking about the actual problems at hand, right? So I think it's a good idea to say we don't actually know.
Well, so when Hubble was launched, we never thought we would see galaxies near the beginning of time, right? So it's the most exciting part about working on a mission, especially the next generation telescope, is how are you going to answer the questions that are going to be 20 years from now being asked? We didn't know anything about exoplanets when James Webb Space Telescope was being built. We hadn't even detected one yet when it was first conceived. So we had no idea. And then all of a sudden exoplanets became this whole new thing in astrophysics. So we know there's planets around other stars. What can we do? Oh my gosh, we have this amazing new telescope. What can it do for this field? And so we actually had to start tweaking our instrumentation. So we put special filters on now, for example, so that we can actually look at these stars where planets are actually going across the stars. Because again, it's a very sensitive telescope, so you can't just look directly at some of the brightest stars where planets are going by. So we have to actually occult that collecting power. But we have ways to do this now. So what's the next thing that's going to happen beyond exoplanets or exomoons or brown dwarfs or binary stars or even black holes?
Yeah, exactly. And who knows, I mean...
And there's things we don't even know,
Yeah, no, and you guys work on the, what is it called, SLS, right? The
Space Launch System?
Yeah, the Space Launch System,
yes.
this fantastic acronym, on the really big rockets. And maybe, one of you guys, when you start working at NASA or at ESA or one of these organizations, you're going to have the opportunity to explore a bit further what would be possible than we do at the moment. Yeah. So I hope for that, because I'd like to see that. I'd like to see, I don't know, a humongous thing just orbiting around the Earth, looking at everything. That would be cool.
Yeah. Planet 9.
Planet 9, yes, exactly.
They're actually on an observing run right now looking for it.
Oh, yeah, absolutely. We keep interrupting these guys.
I'm sorry.
No. Talk. There's no problem in that.
No problem.
But on that subject, how do you really get to work at NASA? No offense. No
problem.
offense.
Hey, you don't have to leave. Well, we get to you have to leave home. Right? But you first.
So I always wanted to work for NASA since I was a kid. When I was 6 years old, I told my mom I was going to be an astronaut or a ballerina. And,
They're similar.
Complete dichotomy.
They're similar.
But so everything I did in school was based on becoming an astronaut. I did a lot of math and physics and science. And when I didn't have another growth spurt when I got into high school, I realized I was too short to be a pilot for the space shuttle, which was a big bummer. So I realized then my only opportunity to go on the space shuttle would be to become a mission specialist. So this is the people that actually do the science. They don't fly the spacecraft, but they do the science in space. And what better science that is completely universal, where you have the complete skills and capabilities to run and operate all kinds of instrumentation than going to chemistry. Plus, if I never got a job at NASA, I could get a job anywhere I wanted, basically, because chemists are very employable. So I saw that as an opportunity, and that's what I pursued. And my research actually took me from, my internship was making wine. I was an assistant winemaker for 3 years.
Oh, yeah. We have to talk. Yeah.
To doing radio astronomy within a year of time. I went from one extreme to the next. And I always had a passion for astronomy and space, so getting to use telescopes, massive telescopes all over the world, was really exciting. It led to all kinds of questions for me, which then led me into doing more laboratory studies and trying to make chemistry that happens in space here on Earth. And NASA saw that as an extremely unique asset, and they actually sought me out to come and help them with research at NASA that's driving the next generation telescope or mission or lander or orbiter or whatever. Mm-hmm. So that's how I started. For somebody that's not an American citizen, there are other opportunities. So we have a fantastic internship program that's open to anybody. So you should be able to apply. It's every summer. It's about 2.5 months, 3 months. So you apply, and it ranges from everything from being a research scientist to engineering to programming, whatever. There's all kinds of different opportunities. So that's one way to really sort of come and experience working at a NASA facility or center. The other way is once you're done with your graduate work is to try to become a postdoctoral researcher there. Then you actually get to do hands-on research at NASA with NASA scientists, or for a mission, or programming, or engineering, whatever. And you get that hands-on experience for a couple of years. So that's another way to actually experience it. But there's opportunities all over the world. I mean, ESA has a number of opportunities. The Japanese, actually, JAXA is becoming quite extensive in research and astrophysics.
I mean, I can actually add a little bit to how you would go about things basically in Norway or in Europe for that matter.
Yeah.
And in Europe, it's a bit driven through the university studies. So if you get interested in space technology or space science at the universities, chances are you're going to meet either a professor or lecturer or other students for that matter who are involved in the right kind of projects. So there's student projects, student-driven projects with ESA, for example. And you kind of glide into this kind of job. And here or there, on both sides of the pond, of course, it's chemists, it's biologists, engineers, it's physicists, it's astronomers, of course, right, who are actually kind of everything together combined, right, exactly. Looking for everything. So, but even also people who are good at media stuff, for example, right? Yeah. I mean, everything. There's a place for everybody in the space industry, and especially in the big organizations, I'd like to say. And in Norway, I would also advise people to look, and search out for the information by the Norwegian Space Center. Or by us from the Andøya Spacecenter, because the Norwegian space industry is a lot bigger than you'd think. There's a lot more jobs than you'd think, so it's worth seeking it out. It's worth looking for it, but you have to still look a little bit for it. But I can personally talk about a student I know from the University of Oslo who started working on probes for sounding rockets when he was a bachelor student, his bachelor degree or his bachelor work. And he developed that particular space probe, which was a so-called Langmuir probe, looking for where you make measurements in the ionosphere plasma. And he developed the whole thing further and further to his doctorate degree, right? Worked on it. It's now the most sophisticated of its kind that we use, at least here in Europe, for the sounding rockets. Makes I don't know how many measurements per second. Is very accurate as well. And the thing I can say about him, or the way I will express what I know about him, is that he probably will never write one application in his life for a job, right? So for those of you who are studying, I suppose the ones who listen to this are students. Seek out the right people at your universities because they are there, and then talk to them, and then you'll find your way into the space industry if you really want to. I promise you that.
On that note, because actually I want to hear more about Andøya, but before that, you, Stephanie, you talked about interdisciplinary science, and I think both of you can say something about this, because I think a lot of us, we're all physics students here. We often get the impression that when you go out and get a job and stuff, you'll have to get really specialized. And you'll really have to get specialized in something, and then you'll be very, not flexible. I get the feeling from the two of you that that's a myth. Is that right?
It depends.
I'm hoping. I'm hoping, of course. But
no, the specialized jobs are there as well. But my impression is that it's actually quite important to not go into these jobs without the fundamental knowledge of all the different sciences. At least, if you talk about the chemical elements and you've been sitting here listening to Stephanie talk about them and you have no idea what they are, it's not good, right? So what I always tell students and also high school students, for example, who are about to make the kind of choices, you can always start with the science, right? And then throughout your studies, through the opportunities that come about, you will find your specialization, and it will come. In my case, it was atmospheric physics. For you, it was the astrochemistry. That will come. That will take care of it by itself. What's important is that you start to learn to think like a scientist. And I think you even said that in your lecture, Stephanie. The moment you do that, you're going to be very attractive for a lot of people, not just in the space industry, but everywhere, from economists to builders. I don't know, because it's a very, I'm afraid I have to say, still a very special kind of thinking. I hope a lot of people will open their minds to scientific thinking in the future. But it's something that has worth in itself. So if you study physics, for example, you start with that. The rest of it will take care of itself just by the opportunities that will be created along the way if you continue studying the basic science, chemistry, physics, or biology.
I also found in my education that even though I was following a chemistry track to be a chemist, I still took classes outside of my discipline, even though I didn't have to, per se. I always took the astronomy classes that I could, or an extra physics class, or an extra math class. Programming, you'd be surprised how much programming you absolutely have to know to be a scientist. And it's not necessarily mandated in your curriculum,
Not yet. No.
which it should be. I mean, you should walk out of here an expert on Python. As a next generation scientist, you should know Python. Everything is going to Python right now. But I can tell you, I still run Fortran code.
Yes. Thank you. So would too.
I just heard from a doctorate student the other day that Fortran was still one of the best on numerics.
Yeah.
Is that right?
So, well, it's still used.
Yeah.
There's a lot of hereditary programs that come from it. And so reprogramming or reconfiguring something from scratch is much more complicated than just building on a working system, right?
Yeah.
They're doing it slowly. So I can tell you, I've also worked with people or on instrumentation that had been operated under Fortran, that it was one student's thesis basically to rewrite that code into C or C++, which now that's obsolete, right? So they should have written it in Python, but Python didn't exist back then. So, but you see where that dynamic is coming, and it's growing, and it's always constant.
Yeah.
You need to know how to program, even if it's not the language
Exactly, yeah.
that you're programming. And today, at least I can take script and I can actually read it, and I can work out the details of what I need to do or how it works. And then you can get these little how-to books or do an online course, and next thing you know, you're an expert. So it's actually knowing how to do what you do, right? And that's what I was trying to tell you in my lecture, is it's not about being a chemist or being an astrochemist or being a theoretical physicist. There's so much interdisciplinarity amongst the physical sciences that it's how you learn, as he said. It's absolutely how you learn, how you think, and how you apply it. And even if it's not in your field, you can actually contribute to a completely different field.
Well, talking about that again, I did want to ask on Andøya, because we hear a lot from NASA. I mean, who are we kidding? But at Andøya, you do a lot of research as well, right?
Yes.
And you said there is a lot of space research being done in Norway.
Oh, absolutely. And Andøya is one of the best hidden secrets in actually Europe, I think, because when people discover that we're there, they want to come and do research normally. It's an island about 500 square kilometers in area, which is filled to the brim with 2 rocket ranges, or 2 places we can launch rockets from, I should rather say, just to be technically correct. There is a laser observatory on the mountain. Actually, I probably chose the wrong picture. No offense to it's a NASA picture, but you could, lasers that you sometimes see, they look a bit like Star Wars, actually. Then we have several radar installations. There are remotely operated flying systems, so drones are developed there. What else do we have? We launch both the smaller I shouldn't say that. We release smaller weather balloons and larger scientific balloons from there and from Svalbard. There's another rocket range on Svalbard that's connected to us as well. It's basically an island that, despite its size, you can't drive for more than 10 kilometers without there being a research station somewhere beside the road. And almost nobody knows about it, because we're hidden away behind a mountain, and that's quite literal, actually. You drive around into a mountain range, or around the edge of a mountain range, and there, boom, is a small, but still rather active and rather good space center that's been doing that stuff. And that's the worst thing about being unknown to most people. We've been doing this since 1962. That's 5 years after Sputnik. They launched the first rocket from there, right? So it's the hidden gem in terms of space industry for Norway, and we have customers that come to launch their rockets. We're a bit like a miniature version of Cape Canaveral, I would say. Right? There's a visitor center there as well. We have a spaceship simulator there. So there, if you just come there and you just want to have and do science for a day, that's fine as well. Right? So it doesn't need to be the hard research. That's okay too. It's just everything's a bit smaller than in North America, or even for that matter in Kourou in South America, where ESA launches its rockets. But it's been there, and it's been there for a long while, doing atmospherical research, traditionally Northern Lights research. But nowadays it's people we have JAXA from Japan as our customers, people from ESA, from Germany, the Norwegians themselves, of course, the universities here, especially Oslo and Tromsø. Just before Christmas, we had guests from NASA. There were 2 4-stage rockets launched from NASA, from Andøya, which were Northern Lights related rockets. So it is, for me as a German, having grown up at a place that was, with 1 million people around me, I came to that place. I didn't see anything. I drove around that mountain. I thought, wow, there's NASA, ESA, JAXA, all the universities. If you don't know about Andøya yet, I would advise anybody to go check it out. And at NTNU, for those who want to know it, I can just mention that there's a course called Space Technology 1 and 2. And Space Technology 2 takes its students, cameraman says he's taking the course, takes its students to Andøya to launch.
I'm taking the course now.
You too?
Yeah.
There you go. So I come to Space Tech 1 to lecture at the university about atmospheric physics, and then at Space Tech 2, the students build a rocket. And we'll probably meet there as well.
Yeah. I think we met last year.
Yeah.
I asked you a question about black clouds.
See? There you go.
Yeah.
Oh, that was you. Okay.
Yeah.
Actually, I remember that one. Did I? But I don't remember the answer, though.
No. But yeah. But I think...
but it is really weird, because nobody thinks about Norway as a space nation at all.
Not at all. But go into the web pages of the Norwegian Space Center just right now, romsenteret.no. They have a great article which basically just sums up this idea. Why don't you actually know that, right? And Andøya Space Center, 1962, that's a part of Norwegian history. It's not in the school books, for example, but one may argue that it should, right? Because at that time, we're talking NASA, we're talking the Soviets, Roscosmos, and then for some reason, little Norway sent its first rocket above the Van Karen line of 100 kilometers, went up to 150 kilometers into the atmosphere. It wasn't orbital, of course, but at that time, then Canada came 2 months later, and then Italy the year after.
Yeah.
But little Norway beat them all to be the third nation. So,
But unfortunately, we are running out of time. But we have one last question.
Yeah.
Everybody has to ask, what is your favorite theorem? Do you have any suggestions?
No one gets to leave delta P before you've answered this. Your favorite theorem? Mathematical.
Mathematical
Or physical?
Or physical, yeah, that's okay too.
Or chemistry? Or...
No.
No.
I'm not sure that I have a favorite one, but what I'm fascinated by is the whole building of quantum mechanics. Not strictly now a theorem stuff, but you have two ways to approach quantum mechanics and quantum physics. You either say, you either think that Heisenberg's uncertainty thing is okay, and then you start going from there. And you can explain the experiment of Stern-Gerlach, where weird stuff happens and spins of electrons. Or you say, I take that electron experiment, I don't want to explain it, I just take it as granted, and then I develop the math from there and go back to the other side. But I'm quite fascinated by the idea that there is no basis. Like you always start with an assumption, take it from there, test it in nature, and it's true. What? So that's kind of my favorite. It's not a theorem, but it's kind of my favorite idea.
Okay.
I hope that's okay.
Yeah, it's okay. So,
My favorite idea theorem has to be entropy.
Oh, yeah, that's
that's a good one.
Because that's my complete life. Everything gets more and more chaotic the longer I exist. I have gone from one project, my thesis, to now I have multiple things going on at any given time. And I only see it getting worse. So.
Yeah, but you had the life cycle of the stars up, right? And at one point, the cloud becomes stars and orderly objects.
Yeah.
We are
But
so
the entropy of the rest of
Not
the
sure what
universe.
that means.
But I also think that's even more chaotic than just diffuse gas,
Oh yeah,
right?
yeah, that's true too.
So-
As I say,
Because then you have to start dealing with
But
living
I'm
creatures.
so
and it's
sorry,
just-
but we have to leave now because
Okay.
people are rushing in. There's a lecture here. But thank you very much for coming,
you.
Alexander and
Thanks for having
Stephanie.
us.
Thank you.
Men etter at du har fått jobben, så kan du velge å fokusere på det du er flink på. Så hvis du er flink til å visualisere noe, så gjør du det. Hvis du er flink til å håndtere ligninger, så gjør du det. Det finnes utrolig mange måter å ta en doktorgrad på. Det finnes utrolig mange måter å oppnå suksess på. Og den typen ting er mye mer individuelt tilpasset enn det folk tror.